Hey, it's your boy Hank here, and with Olivia and Dakota, wherever he's at.
What's up?
We're here to test the law of conservation of momentum, and got our Logger Pro set up. We got our cars all ready to collide and see if the momentum's transferred, and we got our motion detectors here to see how much of the momentum is actually transferred. And that is our project, Mr. Cavanaugh, and you're the best. All right, Hank here with Dak.
What's up, bro?
Liver.
Hey.
And we have our test set up, and to do this, we are using the red car, and the red car is over there, and Dak has his motion sensor down there for the red car. Blue car's down here. Got the motion sensor for it hooked up to my computer, and what's going to happen is when Olivia pushes the car, the Logger Pro is going to record the time, position, velocity, and acceleration, and use that, and then Dak's computer will record the time, velocity, and acceleration used on the red car, so we can see how much momentum is transferred from one car to the other. Alright, for the first test at just the base of the cars with no weight on it, which would be 252 grams, Logger Pro will be used to measure the acceleration, velocity, time, and which will help give us the momentum. Alright, for the first test, I will hit collect on Logger Pro, and so will Dak, and then Olivia will push the car and we'll record. I'll record the blue car and he'll record the red car. Alright, you ready, Olivia?
Mm-hmm.
And that's the first test. And as you can see on the computer, first test, we have at time 0.05 seconds, you have a velocity of 0.006 meters a second. And at position, yeah.
So we are doing our fifth recording here, and we have the 1,252 gram blue car and just the 252 gram red car. And here we go. That was our 10th and final trial, with the blue car having 2,502 grams or 2.502 kilograms, and the red car still weighing 252 grams or 0.252 kilograms. And here we go.
This is the Logger Pro graph for the first car, and to get the average velocity, which is what we chose to use, on the position time graph, you start at where it starts moving to where it stops moving, and then you hit R equals, and the slope is your average velocity, 7.86 rounded to the thousandths. And now for the second one, we did the same thing, but another way to do it is to, on the velocity time graph, you also do where it starts and stops. And then instead of hitting R equals, you hit stat, and you take the mean, which is negative 0.778, but you can ignore the negative, and that would be the average velocity.
So for the first car, which the mass is added to, as you can see, we multiplied mass times velocity to get momentum. And the line of best fit for that one was y equals 0.218x plus 0.216. And for car 2, which the mass was not added to, which was the car that we pushed into, second car, we multiplied the mass times velocity to get the momentum. And the second car's line of best fit is y equals 0.0089x plus 0.1317. Now, all these graphs look alike. They're actually not similar to the scaling, because the scale on this one is 0 to 0.3, while the scale on this one is 0 to 2.3. Back here with Dak. Look at him. He's a cutie pie. Dak, tell us about the law of the conservation of momentum and why the test was not perfect.
According to the law, the momentum should be equal between two objects that come in contact. But ours did not, because we were in a about as imperfect as an environment as you can get. We were not in a vacuum. We had gravity. We had friction, and we had an idiot working with us too. So
That's Olivia,
No, that's him.
the idiot right there.
Here, no, the one recording.
the one who shows up an hour late every time we get working.
That's Olivia.
No, that's him again.
And that's why our results did not come out perfectly like they should
The
have.
idea to measure the law of conservation of momentum was to build a rocket.
And we're here with Olivia, and there's Dakota really close up, trying to light the first test of the rocket with the weight of the rocket and of the rocket fuel equaling 100 grams, and then the object which the momentum will be transferred into in the middle. And boom goes the dynamite. As seen in the little clip right there, our first idea did not turn out so well. Our rocket fuel of potassium nitrate and sugar with corn syrup obviously did not cause a propulsion need to move the rocket. Some possible explanations for this could be that the rocket was too heavy, and also, I mean, just to us, it looked like that the flame caused by the rocket fuel was more of just an explosive flame rather than a steady rocket fuel flame.
And the main reason why we weren't able to continue with the rocket idea was because Hank melted the materials that we were using. When he made his batch of rocket fuel, he decided to burn it in the container we made it in. So when we burned it, the rocket fuel burned at over 3,000 degrees Fahrenheit and boiled the lead container.
And our rocket flew away.
That's for you, Junior. I'm waiting on you, Mark Kavanaugh, Jr. I'm waiting on you, Mark Kavanaugh, Jr.
You suck.
Like I'm saying, can I just start right here?
Let me make it. You can edit the ball in the
No.
air.
Yeah, can I just start right here and take a step back and make it, and then we go from there? I just try that one time. You're not going to want to stand there. All right, let's go. I'm just going to. All right, you ready? Tell me when. All right, start over.
Try number 1,000.